Uh, eh, Sir, one more question, sir. So we have only three timers. So uh, if our application is very complex, like we want different timers for different things. So how?
From my view, using these three timers, you can even implement a RTOS if you are very talented.
Okay.
Even if we have only one timer, we can do. Only thing is how critically you think, how you manage your resources, and then what sort of strategy that you use. These are the key things. Three timers is a very big gift to implement a limited OS. If it is in a very complex, I had seen digital signal processor with maximum 5 timers. That's all. In my experience, I had seen even the digital signal processor is having only some 5 timers. That's all. We don't have because everything is price. And when you implement a peripheral, according to that, you have to maintain other logic states and everything. We have to do those things. Implement, they will, based on they will have some idea. For this much of complexity, we can go for this much of timer. In my experience, I had seen a digital signal processor with 4 or 5. I didn't remember. It was very too long. 4 or 5 timers. That's all. Above that, I had never seen any this one microcontroller or processor with more timers. That is enough.
Yeah, okay, sir. So two or three timers is more than enough for any
More
complex.
than enough to even implement a OS in my embedded system. We are
Okay.
just going to write an application only, no? So in that, how you use them, when to use them is the matter.
Yes, sir.
Then to compare, capture, compare. What does mean by capture, compare PWM modules?
PWM is the power width modulation. So we'll be um, making the digital signal on and off for some
Okay.
time period. Like we're setting the time period.
PWM is nothing but a square wave with different duty cycle. That's all.
Yes, sir.
Right now. That is what the square PWM is. PWMs are used for a different reason, communication, and then to represent many things that we will study in detail. Even in communication, it is used. This serial communication, CAN communication. There we are sending the signals. No, those were actually PWMs only, pulse width modulated signals only. Right. So they carry even information, signals, application signals in them. Right. How do you encode informations in a PWM? That we will study in upcoming. I think we have some idea based on the CAN theory that we discussed. In that we are encoding zeros and ones, no, using a pulse width. Right. So the same concept here. The capture is it will digitize your PWM, will compare your PWM sort of things. So for that there are two capture and compare, and then we also have a PWM modules. Mostly these are like configure and run logics, right? Once you configure, they will work. Then synchronous serial port. CAN is an asynchronous serial port, no? When we want to interface a dedicated CAN controller with this microcontroller, we have to go for this synchronous serial port only. Actually, we are using SPI, serial peripheral interface, right? Which is synchronous in nature, which means it requires a clock signal. There are three important signals: master out, slave in, slave out, master in, and then clock, right? In our case, our CAN controller will be an external one. That external controller, because this microcontroller doesn't have an internal CAN module, we interface that with the synchronous serial port. It is a communication standard in which we exchange the data serially. That is what it is. Also, it uses the clock. If you have that understanding, that is enough. So based on that, using SSP, they have SPI and I2C, both we have. And then universal serial synchronous asynchronous receiver transmitter, USART or SCI, is something like your serial communication, that RS-232 communication. No, to perform that also they have inbuilt peripheral right now, but they did implement the CAN module internally in this controller. We will interface it using SPI, right, which follows synchronous serial port concept. Then there is a parallel slave port. In our project, we used to have a display. In that display only, we display status of ACC, and then because using driver info, and then trip computer value, ambient temperature value, time. So that device you have now, that display. There are different ways of interfacing displays with the microcontroller. You can use the parallel slave port method, right? Using in that you will have a read, write, SIP select control, and then 8-bit line. When you send your 8 bits of data parallelly to that slave module, it will get the data and will display that in display. So we can use this peripheral to interface a display with our microcontroller, right? It is also having brownout deduction circuitry for brownout reset. That means when the operating voltage is below the specified operating voltage. See, if they say 5 volt is an operating voltage, means we have to operate the microcontroller in that voltage. But what I do, I give some 3.3 volt or 1 volt, something like that. In that time, they will make a shutdown. They will detect that there is a low operating voltage. At this point, we should not output anything, because if we do something, that will be error, because our operating voltage is not as per the nominal range. Right, for that they used to have a separate circuitry called brownout reset. So that is also there in this particular microcontroller. And then analog feature, 10-bit.
One question, like for the communication ports. So, uh, why for each this one we have different applications, sir?
Yeah, each one of these circuitry can be used for different purpose. It is not like we have to use all of them to work with this microcontroller. We won't use I2C in our project right now. So we will use SPI SCI, but we won't use ICI, I2C. Right. We will use parallel slave port to interface a display. Right. So these peripherals are available ready-made in that microcontroller. Whether it is applicable to your project or not, that is based on your project nature. So the embedded architect, product architect will decide whether we are going to use that or not.
So each while designing, um, what how we'll finalize the communication, this one, sir?
Okay.
Based on the actuators, like they are taking only is the I2C, they are interfacing only I2C, or based on the actuators
Actually,
only we are finalizing it, or we are taking considering other factors?
see, in a mic, I have a application. There we have a multi-master, multi-slave related stuff. That means there will be more than one master, more than one slave. So that is a requirement of my project. In that case, architect will decide, okay, it is multi-master, multi-slave, we can go for I2C. We can use I2C of this particular microcontroller. But in my embedded project, I don't require, there is no multi-master, multi-slave here. Everybody is multi-master. So if that is the case, I2C is not required for me. If that is the case, though the circuitry there in the microcontroller, I won't use it. It will be there. I won't configure it. I won't use it. But I require SPI. Then I will configure the SPI and will use it. I require SCI communication to communicate with PC. I will use SCI. I want parallel slave port to interface a display with my product. I will use parallel slave port. Right. So what is required for my project, that is decided in this among available peripheral, which one is required. If my project not at all having a display, let's say you are implementing an ACC module, it is not going to have any display. Then you can ignore the parallel slave port. So that peripheral is there, we don't. Did I answer your question first of all?
Yes, sir. Like the interfacing whatever we display or actuators, they will be having also like I2C or SCI. So then that factor is also considered, right, sir?
I2C, SCI, parallel slave port, these are the available peripheral circuitry in this microcontroller. That is clear now.
Yes, sir, clear, sir.
If we configure them, we can use them. Whether that is required, I am going to do an automotive project. That whether my project require those peripheral or not, who will decide it? We will have something called a system design document, SDS.
Yes, sir.
SDS, something like that. In that, architect only, by understanding the customer requirement, technically he will look, the what customer will say, I have two module, they have to exchange the information. If this information comes, this module should do this. Like that only customer will say. He won't say you use CAN, you use I2C, you use SCI. No. And then he will say, okay, I want to see the album status or a street name in a display, ACC status in a display. So like that only the customer requirement will be more generic. He won't ask you implement it in CAN, FluxRay or most Lin like that. As an experienced people, the architect or embedded system engineer should decide which we can go for. Okay, he is asking us to, he want to exchange information between module. Okay, so it is a automotive, then we can go for CAN because it is very robust, proven, so we can use that. Some other customer comes, I need to have a steering wheel buttons, I need to have in my steering. When I press that button, something should happen. So immediately that particular embedded system engineer, okay, this is little bit a slow operation, we can go for Lean, which is less speed than CAN. So these decision will be taken by the embedded architect, that means the product architect or an embedded system engineer. If he is a small scale, like the embedded system engineer itself will decide that. Do
Yes,
you
sir.
understand what I am trying to say, or you have doubt?
Uh, yes, sir. I have understood.
Let me ask you the questions in this way.
Yeah.
When a project comes to the automotive engineer or an embedded engineer, it says you have to display ACC status in a LCD display or a TFT display. This is the requirement, right? If that is the case, the embedded engineer should immediately check how we can interface a display with a microcontroller, yes or no, right?
Yes,
There
sir.
are many methods. There are certain display, you can interface that serially using SPI. There are certain display you can use a parallel slave port PSP method. Using that you can interface. So he may also specify the display should be in blue color, or display will be a normal lightweight display. It doesn't have much feature in it. It should be low cost. Like that the customer will say. Immediately embedded engineer will take which low cost display has PSP support, or which display has SPI support. We can interface that with a microcontroller. Whether the microcontroller has a PI peripheral to interface that display with that. Whether the microcontroller that we choose has a parallel save port support or not. So he will think what is available in the microcontroller, what is the customer requirement. To achieve the customer requirement, what is the object or a part that he should choose. That means what a part that he choose means what LCD or whatever the peripheral that he has to choose, and then whether that supported standard, how we can interface that particular part with microcontroller, right? To interface that, whether we have enough peripheral available in the microcontroller right now. Based on that only the selections are made, right?
Yes, sir.
So
So, yeah, yes. Now I got it, sir.
it is purely based on the customer requirement, choosing the microcontroller, choosing the display, choosing everything. As the microcontroller having the I2C, they cannot go and implement the I2C. For that, the customer is not happy about, right? There are some projects it doesn't require even I2C at all. In that case, they won't choose the 16F877A itself. They can choose another low cost controller which is having what the customer want. Understood?
Yes, sir. Got it.
So the selection of microcontroller and then part, everything is purely based on the customer requirement. What the customer comes up with, based on that we have to check different possibilities. What we can go for. What challenge, if we use that, what challenge we face. So like that we have to think, according to that we have to choose. Make sense?
Yes, sir. Yes, sir. Got it, sir.
What, Amir? Understood?
Yes, sir.